once again, let's take a look into an example so we can see this theory into practice. So let's assume that we have a signal X that is composed by these numbers here, so 5, 6, 7, 8, 9, 10, and then we will use n equals 3. So what we will have, we will get signal blocks X of m with m in a range as we needed to fit the signal. So we have n3, so we have x0, it will be 5, 6, and 7, and x1, it will be 8, 9, and 10. So the polyphase elements of x n of z with phase going from 0 to n minus 1, they are given here. So it's n equals to 0, n equals to 1, and n equals to 2, so n equals to 3 minus 1, so 2. And then we have the polyphase elements, so we have 5 plus 8z to the power of minus 1 for the phase 0, 6 plus 9 to the power, times z to the power of minus 1, this is the phase 1, and 7 plus 10 z to the power of minus 1, and this is phase equals to 2. And this can also be written as polynomials or blocks that is given here. So we have block 1 and block 2, then we have 5, 6, and 7 times z to the power of 0 plus 8, 9, and 10 times z to the power of minus 1. So both things here are equivalent. And the polyphase vector of z has all these components, so we have x0, x1, and x2, and it's just replacing here. This is the polyphase vector x of z. So now let's assume we have the first analysis impulse response, that h0 is 3, 4, 5, 6, 7, 8, and if we continue using n equals to 3, then its polyphase vector in general will be given in this format here. So here we see that we have n equals to 3, and n minus 1, n minus 2 until 0, and here's the subband k. So with our phases, they're going down, and then for this example, so we will have 5 plus 8 times z to the power of minus 1, 4 plus 7 times z to the power of minus 1, and 3 plus 6 times z to the power of minus 1. So this is what happened in the analysis side. On the synthesis side, there are also equivalent operations we can do, and we can use again noble identities to exchange filtering and upsample of each subband. So again, if we take one subband and we have upsampling and filtering, we can use noble identities, and we have filtering and then upsampling. And we see here this parallel with the z to the power of minus 1 elements. So we will have also the polyphase matrix for synthesis. This is a type 2 polyphase, and each filter has its polyphase components along the rows, and each subband filter can be written at this equation here, where we have frequency and phase, and this sum here. And the output of the synthesis filter bank will be the subbands here. This is the filters of synthesis, and here it's equal to these here. So we have our input hat, which is the output, so it's reconstructed. It will be y, this is from the analysis part. Here is our synthesis given here, our matrix. It is equivalent to our input times h of z. This was our analysis that we've seen here, times the synthesis, which is here. So again, this is the output of the synthesis filter bank. It's equal to the subbands times the filters of the synthesis, which is equivalent of the input times the filters of analysis times the filters of synthesis. So perfect reconstruction results if we have G of Z, or synthesis, is equals to the analysis plus times a delay. And Z of minus Z is a delay. Since by substitution we will get that x hat, the output, is equal to x of Z, our input, the analysis times a delay, C to the power minus D, times the inverse of the analysis. So we see that the output is equal to Z of minus D, a delay, times the input. So observe that perfect reconstruction requires only a matrix inversion. The problem is how to invert a matrix of polynomials. So one example for the construction of H of Z, so how to obtain an H of Z which only has the first coefficient of our polynomial unequal to 0. So we will design our impulse response H of k such that the H of k of Z has no higher powers of Z. Hence, only the first block of our impulse response can be unequal to 0 and is limited to a length of n. And that's too short.